Hi everyone. Okay, welcome to my lab. So for this lab, we are going to talk about how to use some bioinformatics tools to run analysis for the single-cell RNA sequencing data. I guess you guys has already touched all the details about the methods about how to run analysis for single-cell RNA sequencing data and also the history about develop this technology. So for this week, we were going to focus on mainly the R package called Seurat to run analysis for the single-cell RNA sequencing data. Just a few announcements before our lab. So I would hold an additional office hour since this week on Friday. It's on each Friday the afternoon at HSPH Building 2, Room 428. So feel free to find me if you have questions for me and also about our courses and about our homework. And please double check again you have access to this Odyssey pass because we would need the files saved on this folder for homework 3, 4, and 5. If you didn't, please shoot me an email. And another announcement is that homework 3 might be due on Sunday midnight, so just take your time. So for the outline of today, I know 80% of you guys are graduate students, and both our graduate students and undergraduate students are heavily exposed to some to research. So I would provide you some useful techniques for running jobs on Odyssey while doing your research, especially when you are dealing with some really large scale data. And then our main part is about how to use the Seurat to run analysis for your RNA sequencing data. And then I would take you guys to go through all the questions one by one to complete your assignment. Feel free to stop me or give me any comments in this process. So so for this Odyssey Fest, the problem we have to touch now is that when you are doing the research, especially when you are dealing with some really bulky data, the chances are that you might encounter some really large scale data while you have to run multiple jobs on the same large scale data set. For example, when you might store 24 chromosomes information into one large scale data, and you have to run analysis for each chromosome separately. So at these circumstances, you might want to create 24 jobs. 24 multiple jobs to run on the same large scale data set at the same time. But if you store the large data on the Odyssey system, the chances are that when you run all the jobs, those 24 jobs might lock each other, and which might reduce the efficiency of running jobs. So how could we solve this problem? This is actually due to the problem of the high I/O efficient, which means you just give too much burden for the input and output of the system. So to solve this, we could do some improvements when we were saving the data on the Odyssey system. So as I mentioned for the last lab, the Odyssey just is composed of a lot of nodes for running jobs and do computation, but this is the same for how they store their data. So actually, they adopted a distributed data store saving strategy. So with this command called as lf-strip-c, you could actually cut your large scale data into very small chunks and send each of the chunks to very small nodes on the Odyssey system. So for here, this is 18 numbers dash c followed by 18. Number 18 means that you cut the large scale data into 18 small chunks and store each chunk into one node distributed across the whole Odyssey system. And when you were trying to get access to this data, actually now you can run 18 separate jobs on the same large scale data, and it wouldn't influence your efficient. Well, an additional. You could take it as a bonus for for this lab. You don't need it for this homework, but I think one day that might be useful for your research, especially when you are dealing with large scale data. So feel free to find me to talk about it. I think we could explain it more clearly while we were face to face. Okay, then the main part is about how to run the single-cell RNA sequencing analysis based on the R package Seurat. So please double check whether you have already installed all these packages. If you have do so, just jump this step, and then we could library the package that is necessary. So for this exercise, we will be analyzing a single-cell RNA sequencing dataset of PBMC from the 10x Genomic platform. They got a tutorial for this one, and you can go to their website to check. They just updated their version of the software from version 2 to version 3. So there are some updated changes. For example, originally they store all their dataset into a .rds object, but currently they just changed the data structure. We can see the new data structure in our homework. Yeah, we can touch that later. Just pay attention to this command while you are doing the homework question 1. So if you read in the original Seurat data, you can view their data structure by using the dimension command. That would give you actually the number of genes as the number of rows of the raw data, and also the number of samples, which is the number of the cells, as the number of columns in the raw data. So you can type both of them to get the dimension information, which is needed for your first question. You can also print out the row names of the raw data, which is actually the gene ID. If you need some downstream analysis, such as the gene oncology, this information would be useful. So you can see for our lab material, the actual Seurat object contains a Seurat object with 2,000 samples with 32,000 genes. So this sample sets include roughly 1,000 PBMC samples from 2 different batches. All right. But one question is that if you type this PBMC add command, you might see that there are multiple data sets stored under this PBMC. They are called as data, raw data, and also the scale data. So what are the differences between them? We might wonder the actual data structure behind them. So to understand them, actually they have some differences. So for the raw data, it actually represents the original expression matrix, with the row names represent the gene names and column names represent the cell names. Well, you can call it as sample names. So actually, basically, it's a count matrix with either row counts or normalized one, such as the TPM and FBKM. But the input expression matrix should not be log transformed, so it contains basically positive values. But for data, it's actually normalized or log transformed single cell expression data. You could type help normalize the data for more information. So this is actually a measurement of the relative abundance level of all genes, and it is frequently used for the visualization steps such as the volume plot and the feature plots, which are both very useful for your homework. And so since it's log transformed or normalized, it could either be positive or 0. And for the scale data, you don't need to care too much about this data type. So they can be displayed in heat maps, so only useful in the heat map, and they could either be positive or negative. Okay, so if you could jump back to our lectures, yes, just a very brief review. So in the lecture, Shirley might have introduced you the history of the technology, and in the introduction part, and how they are developed in the past 10 years. And then is the main part about our about how to run this analysis. So actually, for now, we are trying to do the quality control step and also the visualization step to get familiar with the original dataset. And our alternative goal is to cluster all the cells into different clusters, which might represent the actual cluster of each of the cells. And then we might find some really statistically significant biomarkers within each cluster. And based on the information provided by these biomarkers, we could give them different annotations, such as different type of cells for each cluster, and this is our automatic goal. So before we are doing the quality control, we might do some initialization steps, which means how to tidy the dataset. So if you type in the command as object.size to check the actual storage that the original Seurat data take, it is very large. Well, not that large, but not quite efficient when we were doing the data manipulation. And both the this problem is caused because the single cell RNA sequencing data is very sparse, which means it contains a lot of zeros. So when you finished your first question, you might see that the dropout rate for the original dataset is really, really high, around 97% or so. So if we want to do the analysis more efficiently, we might have to filter out some poor expressed cells or poor expressed genes. Sorry. So the threshold might be that we might only keep genes expressed in larger or equal to 3 cells, and we might also keep all cells with at least 200 detected genes. So how could we do that? We could simply use a command as create Seurat object. Well, as it's suggested by its name, it's actually create a new Seurat object with some specific threshold. For example, if you set the threshold as the min dot cells equal to 3, that means you only want to keep genes expressed in larger or equal to 3 cells. And if you keep the min dot genes equal to 200, that means you only keep all cells with at least 200 detected genes. And the project equals followed by the 10x PBMC, just refer to the data structure that you want to use for this command. And after create the new Seurat object, you can view the dimension of the data. So actually, compared with the original one, it's much smaller now. It's about 1/3 of the original data. And if you check the storage, they become much smaller here, and so more easier for running the following analysis. This step might be very necessary. And after doing that, we might do some quality control. So to do the quality control, basically is to find some potential confounders which might cost some stratification for the PCA analysis. Yeah, so some potential confounders might be the number of genes and the number of the unique molecular identifiers. So for this QC, the first step might be filter out cells based on the percentage of mitogenes presented, and the second step might be filter out cells as potential multiplets. So how could we do that? We could basically just visualize the gene and the module counts and plot their gene and module counts relationship, and exclude the cells with a clear outlier number of genes detected as potential multiplets. So first step is to grab all the mitogenes within our original dataset. To calculate this, the package has actually created a list of mitogenes stored in their original package. You can grab all the mitogenes from your dataset by using the grep command. And then you can check how many mitogenes you have by using the length command. And you can calculate the percentage of the mitogenes over all the genes in your data. So this might be the answer for the question 3. Yes, I guess it's question 3. Yeah, we'll talk about that later. And then for this step, actually you can view the distribution of the percentage of the mitogenes. So you can see the main parts are accumulated around less than 0.1. It's about 0.02 or so, and some genes with extremely high percentage of mitogenes might be considered as a potential outlier. So you can do the same thing for the number of genes and also the number of UMI, which is the number of unique molecular identifiers. So all these plots are just to give you some intuitions about the potential outliers of your original data, but actually up to now, they haven't done anything to remove them. And you could go further to see potential outliers by plot the percentage of the mitogenes against the number of UMI, also by plot the number of genes over the number of UMI. So I would suggest that this plot might be very useful because you can see that these two very clear outliers are separated too far away from the main distribution part. So it also provides you some information about how to set up the threshold to filter out these genes. For example, you might consider filter out cells with expressed genes larger than 2,500 here. So, and you might also set your low threshold as like around 100 and 200 or so. So all these three plots actually provide you some information about the threshold that we might adopt it to filter to do some initialization steps and filter out some potential outliers. So this comes to this command, which we call it as filter cells. So it filtered out some potential problematic cells with poor quality. So what we adopted is here the low threshold as the number of genes as 200, which might be at this corner of the plot, and the high threshold as 2,500 at the right corner of this plot. So this combined command means that you don't want the lower threshold less than 200, and this this command here means that you might set the threshold as like 2,500.05 or so, but actually it makes no differences here compared to the simply 2,500. Okay, so this would be useful for your second question, I guess. And then before, so now we have to do the QC, and just a quick reminder, we might want to do some linear dimensional reduction method and also the nonlinear dimensional reduction. Yes, a quick question for you guys is that what's the difference between the PCA and the TSNE? Okay, you might take a while to think about that question. So because it's a very important one for our courses, especially for this chapter. So PCA might be considered as the linear dimensional reduction method, and the TSNE might be considered as the non-linear dimensional reduction. So before we have, so the remaining part is about how to run these two methods to analyze, to cluster all our cells into different groups, and then we do the annotation for each group to see what type of cells we have in our data. Before we do that, we may want to normalize the original data set. It's very simple by doing this in the Seurat. So just type in the simple command as the normalized data and the subject you want to normalize, and the method as the normalize, and also the scale factor. Actually, it employed a global scaling normalized method by default. So basically, it normalized the gene expression measurements for each cell by the total expression, and then multiply this by a scale factor. So by default, it's 10,000. You can change the default value, but it's highly recommended because when you use this value, you might keep as much information as you want. So after doing the normalized part, if we could go back to our slides, we are now coming to the cluster part. So this is all about the QC method and also the PCA and the principles of the TSNE. So now we want to do the clustering, but before we do cluster, we want to see what type of information we want to use to do the cluster. So the information might be provided by all the genes or all the cells. So actually, it's not possible. So we have to detect the variable genes, which is actually differently expressed across different type of cells. So this step is called the find variable genes. So the Seurat has already got a simple command as the find variable genes here. And you could use this default setting because after doing this, it could keep around 2,000 genes or so, which could provide you enough information to detect the significant PCs that you might want to use for the linear dimensional reduction. After doing this step, you might see all the variable genes with the labels in their plot. Well, it's a busy plot, yeah. And you can type the length of the variable genes to see how many genes you have keep for finding your PCs. And you can also type all their gene names here. So after doing this, we could use the variation provided by all the variable genes to calculate our PCs or do the t-SNE or run the t-SNE. But the problem is that the variation might not be quite reliable as we expected because it might contain some unwanted source of variations, which might include the technical noises, the batch effects, we talked about that in the second week, and also the biological sources of variations, such as the cell cycle stage. Well, you would touch the cell cycle stage in around question 5, no, question 6. We'll go back to that later. So all these sources of variations that we don't want, we could call it as confounders. So you might have touched the confounder concepts in some other courses. If not, never mind. So actually, we want to exclude the influence of all these confounders from our current variations provided by the variable genes. So it's in the Seurat package, it's done by using the command as the scale data. So in this command, in this combine command, actually you input all the confounders you want to regress out from your current variable genes. So the two main confounders we are thinking about are the percentage of the mitogenes and also the number of UMI. If you want to go further to regress out the unwanted information provided by the the cell cycle, you could also change these two indicators here as the cell cycle. This might take several minutes, and after regress all the noises out, you can run the PCA to find the top significant PCs. So for now, we have already done the PCA, but we might want to visualize the results. The tricky part is that when you cannot visualize the all dimensions of PCA in simply just like 2-dimensional plots or 3-dimensional plots. You have to pick some PCs. So how to pick some PCs to visualize your data? For the Seurat package, it actually have a lot of methods. So basically for the first one, you can simply print the PCs, which would give you all the significant PCs you want. For example, for here, I print out PC1 to PC5, and also the genes that the top genes that contributed most significantly to this PC. For example, for PC1, gene CST3, FCN1, AIF1, TYROBP, and S100A8 might contribute a lot to the first PC. I guess one question is asking you guys to print out the name of the genes that significantly contributed to this PC. And so are for the remaining PCs. So these are basically just the literature information. You can also visualize them by some intuitive plots. For example, this PCA could give you the information about the genes that could be separated by this specific PC. So PC1 could separate the genes on the left hand and the right hand very well, and PC2 could separate the genes on the left hand and right hand very well. And you could also plot the PCA by using the PCA plot here. So now, since you didn't do any, since you haven't do any annotations, you can't see too many patterns from this PCA plot. But the PC heat map I might suggest is very useful because if you type all the 12 top PCs heat map, you can see that from PC1 to PC4, they give you many clear modules, and which might mean that they could do very good job when different when differentiate the genes from each other. But for the remaining PCs, such as the PC9, it's quite noisy and you can't see any patterns. So they may not be considered as the top significant PCs that might be used for your clustering issues. So more quantifying way might be using the Jackstraw plot. Actually, it's comparing the distribution of the p-values for each PC to a uniform distribution. So the uniform distribution is displayed as the 45-degree line here. So if the distribution of the p-value of your PCs are dividing so too far away from this line, that might mean that this PC could provide very useful information when doing the clustering. So you can check that the PC 1, 2, 3, 4, 5, 6, even until PC 9. Yeah, PC 9 is not quite so because they overlapped too much. Even until PC 8, all these PCs might be very informative for your clustering analysis. You can also plot the standard deviation of each PC across all PCs. You can see that they got some very strange change around the 7th PC, 8th PC, or PC9. So you might want to include all these 10 PCs into your clustering issue. So this is what we were doing now for running the clustering. We are using the first 10 dimensions to do the PCA to find the clusters. And by using the finding cluster command, you can cluster all the cells into different groups. So for questions 7 and 8, and you might be asked to change the resolution of the principal components or the t-SNE part to see whether the result would change too much. Okay, then that's for the PCA analysis. The second part is to do the nonlinear dimensional reduction part as the t-SNE. So t-SNE might be more simple now, but for t-SNE, you have to set the seed set the seed before you do the analysis. But actually, this command wouldn't work because for the run t-SNE, if you can check, you can type help run t-SNE in the R section. You might find that they have a default setting to change the seed parameter. So you don't want to change the seed parameter here. You want to change it within this command. So it's called use seed.use. Yeah, you can check it in my annotation for your homework. Then this means the dimension you want to use, and after running the t-SNE, you can show the t-SNE plot. But now, so for now we have completed the clustering issues. So if you go back to our slides. Yes, we have already do the clustering issues, and the final part is about to doing the annotation. So for now, you only got the number of the groups, but you don't know which group identify which type of cells. So the last step is to do the cell type annotation. To do that first, you have to find the significant biomarkers and could identify the specific cluster from the remaining part. Yes, this part is about identifying the cluster, identify all the biomarkers. Well, I will touch the following part in the second part of our lab. So just remembering that we stopped here by finding all the clusters for our genes. So and then the last job is to do the annotation.